Yes, can someone tell me what we studied in the last class? Yes, I'm waiting for a response.
So we are done till decoders, 2 to 4, 3 to 8, and 4 to 16.
Exactly. Uh, Thank you for the response. So today what we will do is we will continue with, you know, I hope all of you are able to see the screen, right?
Yes, sir.
Yeah. So, this was the last thing that we discussed, right? 3 to 8 and, you know, we had seen the simple block diagram, right? Where it has n input data and enable inputs and how many possible outputs, right? All this we had discussed and how we use 3 to 8 decoders, okay, for creating 4 to 16 decoders, right? Okay. So, yeah. So continuing our discussion, we will look into today implementation of full adder circuit with uh, decoder and two OR gates. Okay, suppose a question is asked like that. Okay, how will you implement a full adder circuit uh, using your decoder and two OR gates? Okay, so as usual, you will be taking off your three input combination, okay, which is from 000 to 111, and then the carry and the sum responses, right? Where it's going to be low and where it's going to be high, right? So accordingly, you will see that your carry is high when there are two ones in your inputs, right? So the sum becomes 0 and the carry becomes 1, right? So similarly, I get my carry values and the sum values. Now, if I have to put this in the form of, my function, then what I will do is a function of xyz, okay, and summation 1 2 4 7, okay, wherever it is corresponding. Here at 1 it is corresponding, then at 2 it is corresponding, or I'm getting an output, then I'm getting an output at 4, right? And then I'm getting an output at 7, high values. So we are looking at high values and those numbers are written here as 1 2 4 and 7. Similarly, if you look for carry, okay, you will see that you are getting high values for 3, 5, 6, and 7. So 3, 5, 6, and 7. Right. So here you're getting your high values. So once I have this, what I can do is I can just use this technique also, which I have drawn here. Okay. So I have X, Y, and Z. These are my inputs and my decoders. So since I have these numbers, it's very easy for me to decode it. Okay, so sum should be connecting to 1, 2, 4, 7. So if you see that, okay, I have a sum here, and this should be connecting to 1, 2, 4, and the other line is coming here 7. Right. Similarly, your carry will be connecting to 3, 5, 6, and 7. Right. So I have used a decoder. Okay, here I've used a decoder and I've used two OR gates, sum and carry. So since there are three inputs and a total of 8 minterms, we need a 3:8 decoder. So that is how you will decide how many you need. Okay, you have how many inputs here? 3 inputs. So based on that, you will decide how many decoders. Now see the question here, they have just told you to use a decoder, but they have not mentioned specifically that you have to use a 4 is to 16 or 3 is to 8 or uh, 2 is to 4. So similarly, you will have to decide, right, based on the number of inputs as to that how many what line decoder that you will be using. Okay, so is that clear, students? Till this concept, is it clear? Any doubts as to how we got this?
No, sir.
Okay,
Sir.
fine. Thank you. So you have an implementation of full adder, okay, with a decoder. The other application now, what we can also do is, we can implement the mux. So before understanding what is a demultiplexer, you should know what is a multiplexer. Okay, multiplexer is actually used for combining different signals. Okay, say you have n number of signals at your input side and you want one particular signal to be at your output. So you can decide as to which signal of your input is passing to your output. Okay, so the reverse of that. Okay, so mux will have multiple inputs and single output. Demux will have, okay, the reverse of it. Okay, fine. So wherein you'll have single input and multiple outputs. Now let us take this truth table. Okay, so I have A, B, and I have enable. E is nothing but your enable line, and I will have D0, D1, D2, D3. So what I will do here is I will just have the enable, okay, one, then AB is going to be don't care, then 0, 0, 0, 1, 1, 0, 1, 1. Okay. So when my input, okay, when my input is going to be 0, 0, D0 will be highlighted. When it is 0, 1, which is 1, so D1, okay, D1 will be 0. Okay, when it is 1, 0, then 2, it is 1, 1, then 3. Okay, so it is the reverse. So what we can see here is these are your select lines.
Sir,
yes, yes.
Initially you had said when enable is 1 only, then we take the output. But here enable is 0, then
this
we
is
are
in
taking the
demultiplexer.
output.
This is in demultiplexer. That's what I told. It's the reverse of.
So, but enable shouldn't affect, right? Enable is like a switch.
That's what. See, it is how we want. We can design. Okay, it is how we want. We can design. If you want it to work at 0, also it can work at 0. Ultimately, you are designing the circuit, isn't it? So I am considering this. Okay, I am considering this. So which means whenever my input is 0, okay, whenever my input or my enable is 0, I am just concentrating now on the select line. So this is just an application. The most important thing that you have to remember here is how to design a full adder circuit with decoder and 2 OR gates. So decoder is done, 2 OR gates is done. So this is just an application as to how you can application oriented. Okay, this is not for your syllabus point of view. Okay, so I'm telling if I put enable is 0, okay, enable is 0, and I can design my truth table in such a way that if it is 0, 0 here, AB is 0, which means D0. So similarly D1, D2, D3. Okay, fine. So here A, B, and enable. It is like enable passing through a inverter. Okay, so I give 1 here, and then it passes through the inverter. So I give A here, it passes through double inverter. B passes through double inverter. So what is happening? Whatever is the value, it has been replicated the same. But with regards to E, as you told, okay, what is going to happen here? Whatever values are given, I'm giving the reverse. Okay, why is that I'm giving a reverse? Because I know that I am going to put an inverter here. Internally, there is an inverter here. Okay, so that's the reason I'm giving in this fashion. And I will get D0, D1, D2, D3 as my outputs. Have I cleared your doubt? Is your doubt clear? Is your doubt clear? Can I move on?
Yes, sir. Yes, sir.
Okay, fine. So since I know what is inside, okay, then I will be actually, it is my wish. If I do not want, I can remove this inverter here, okay, And I can use the other way that was mentioned, okay, which means 0 here and then all 1 1 1 1. That's also fine. Since I'm using an inverter here, I can even reverse it. So it is my logic, my circuit, and my way of designing. So anything can be done. So that's why it's called a logic circuit. Okay, fine. So those were about your decoders. So today we will start off, okay, with something called encoder. So encoder is the reverse. Okay, maybe you have a message, and that message has to be, you know, there should be some code to that message, so that in between the channel, the message is encoded, so that if someone else is listening, okay, eavesdropping, then it should not be easily understandable. Okay, so that's the reason we use this encoders and decoders. Okay, so this is how we actually use for the purpose of communication. Now here when you see encoder, okay, so let's go through what is an encoder. An encoder is a digital function that produces a reverse operation which a decoder does, right? So encoder will have 2 raised to n input lines, but this 2 raised to n was where at the output side. So just if we go back and you see the block diagram that I had shown you earlier, right? You have 2 raised to n at the output side, but you have n input lines at your input side. So n is here, 2 raised to n is here, right? But for our encoder, it becomes the reverse. 2 raised to n comes at the input side and n at the output side. Okay, so the output lines will get generated. So just have a look at this truth table here, where you can see, okay, we have from D0 to D7, so which means 8 inputs we have, right? So we call it as octal to binary encoder. Input lines, and the output lines generate a binary code for 2 raised to n input variables. Example that I have taken here is octal to binary. Now how does it work? Now let your concentration be only on this truth table. Okay, so as usual what I will be doing here is, okay, uh, my inputs, okay, if D naught is high, okay, if D naught is high, then rest all will be 0. So which means all my x, y and z should be 0. D1 is high, okay, rest all will be 0, and I should have only 1 here, right? So it is like binary 0 1 2 3 4 5 6 7. So let's take the value of 7. 7 is here. So once D7 is enabled, whatever is below that, okay, D6 is below D7, right? So what I meant by below is D7 is more significant bit, okay, than your D6. So D7 has a higher priority than D6. So if in case it is in this fashion, then whatever is the value here, okay, it becomes don't care. Why is it don't care? Because I will consider the value which is the highest. That's why it is also called as priority encoder. Okay, this encoder is also called as priority encoder. Now let us take one more example. D2 is higher. Okay, so I will consider something which is higher than this. So which means I will check for values if it is 0 or it is 1 or it is 0 or it is 1. Something below this, what I will do is I will neglect it. Okay, so towards your LHS, this all becomes your don't care. That's why I've written X here. X is nothing but your don't care terms. Okay, and we will be using this don't care terms for, as I mentioned, priority encoders. So ultimately you should see wherever you have ones. Okay, now see the first case here. In the first case there are all zeros, there is no one at all, right? You have D0 0, D1, D2, D3, 4, 5, 6, 7, all are zeros. So in that case you will also get an output 0, but it is invalid. Why it is invalid? Because none of the D parameters are enabled. In the next one you see it says it is valid. Why is it valid? Because one of the terms are high. One of the terms are high. So which is that term? That term is nothing but your D naught. So D naught is high. So if one of the terms are high, then it gives me a valid output. So this is telling me it is not a valid output because all are zeros here. D0 to D7, all are zeros. So I hope you have understood the truth table. Any doubts in the truth table? Students, any doubt in the truth table?
No, sir.
Okay, fine. Thank you. Now we will move on. Okay, so we are concentrating on those things which have valid outputs, right? Next what we will do is, okay, we will see as to how to get this circuit. Now D0, if you see, or D1, okay, D1 if you see, it is X, Y and Z, right? So what we will do here is, actually we have to create one more truth table. Okay, I've written make two truth tables with zeros in inputs and no valid column, okay, and don't care in valid column. Okay, fine. So X, Y and Z. So X is nothing but wherever I have high values. Okay, high values wherever I have to take that. So D4, okay, D4 is higher. Okay, see X wherever X is high. So X is high here. X is high for what? D4, when D4 is high. Okay, next X is high when D5 is high. Okay, X is high when D6 is high. Similarly D7. So my X value is going to be 4, 5, 6, 7. It is just like, you can even write a function or summation. Okay, and you can put in the bracket, okay, 4, 5, 6, 7, just like how we did here. Yeah, just like how we did here. The same fashion you can use it here. So X becomes my D4, D5, D6, D7. Similarly, Y also you can see where are the high inputs. Okay, so Y is actually corresponding to D2, and then it's corresponding to D3. Okay, and then it's corresponding to D6, D7, right? 2, 3, 6, 7. Similarly, I get Z. Now, how do we connect them? Okay, D0, D1, D2, D3, D4, D5, D6, D7. So I should be connecting 4, 5, 6, and 7. So take the fourth one here, 4, and then 5, okay, and then 6, and then the seventh one gets connected. So this is how you get your circuit, your logical circuit. So inputs are here, D0 to D7. Okay, the reason why D0 is not connected anywhere is because I don't have a valid high value towards my output. So that's the reason D0 is not connected anywhere. So either you leave it or you just keep it, that's fine, doesn't matter. The only thing that matters is from D1 to D7. Okay, so what is written here, note that the encoder assumes that only one input line can be equal to 1 at any time. Okay, so here this is assuming that if D1 is high, as I mentioned previously, no other values are high. That is what we have done an assumption. Okay, so I cannot have D1 and D2 both high at the same time. Okay, that is what we are trying to say here. So I am trying to get a code here. What code is it? It is nothing but D0. So this 0, okay, 0, I'm making everything as 0. 1, I'm taking only 1, binary 1 here. So that is the kind of code that I am creating. So when I see these outputs, okay, when I see these outputs, I can take X, Y, and Z separately and create my logical circuit. So once I have my logical circuit, it functions as the truth table. Because what is a truth table? It's a relation between your input and output, right? It creates a relation between your input and output. Fine. Otherwise, the circuit has no meaning. The circuit has 8 inputs. That is, it has how many? 256 combinations. Only 8 have meaning. The others are don't care conditions. Now, if you see here, only 8 values. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So only these 8 combinations are having meaning. The other combinations, okay, the remaining 256 minus 8, the other combinations about 248, right? About 248 combinations are meaningless. When I say meaningless, they have the valid column is 0. For that particular row, it is 0. Okay, so these are the only needed ones. Okay, these are the only needed ones. I hope you're understanding. Any doubts here, students? You can always ask me. Any doubts, students?
No, sir.
Why am I considering only these? I have 256 combinations, right? So why am I considering only these? Yes, can someone respond? Why is it so? Because
Because we need only one high input.
exactly. So wherever we need high, only that we are considering, right? So that is what I have given here. So apart from this, if I don't have one, what will I get? I will actually get a 0, right? I will get a 0 like this. So if I get a 0 like this, then what's the pointer? Is there any point in considering that combination? No, there's no point. So I am considering those input combinations where only high values are there. Okay, fine. So this is how I get X, Y, and Z. Okay. So the remaining about 248, yeah, about 248 combinations, I will have no meaning, so I will not consider them. That's it. The above mentioned encoders are not available in IC packages, okay, since they can be easily constructed with OR gates. So I do not have a ready-made IC prepared, to do this function. So instead, I will have to do it with the help of our OR gates. Priority encoders are the type available in IC format. See, normally what we do is we do not just create or manufacture IC chips. Okay, only if it's standard, only if it's really needed, then only it is manufactured, because manufacturing an IC is really a big task. Okay, and bringing everything together, and lot of chemical compositions involved, a lot of purification of sand is needed. Zokrasky process, have you gone through Zokrasky process in your chemistry classes? Have you come across this term?
No, sir.
No. Okay, this is a kind of process where the sand is purified. Okay, so it is a chemical process where the sand is heated more than 1000 degrees. Okay, it's brought into molten state, and once it's brought into molten state, all the mm, impurities are all evaporated, and then there are various processes. Okay, today if possible, okay, I want you all to look into something called CZ process. In short, Zokrasky process is also called CZ. Okay, so try to have a look at this process. It's very interesting. Okay, how sand is purified to about 99.9%. Okay, so once it is pure, then only IC manufacturing starts. Okay, fine. So here, what we will do is we will try and understand these priority encoders. Okay, so priority encoders are standard form, and I will have ICs for them. Okay, from 0 to 2n minus 1. Why is it 2n minus 1? Because we have 2 raised to n types of inputs, right? Okay. Only the highest priority input line is encoded. Only the highest priority. Okay, as I mentioned previously, with regards to your truth table here, only the highest priority. The lowest are all treated as don't cares. X is don't care. So it can either be 0 or it can be 1. So if my D6 is enabled, I will not see anything below that. I will only be bothered above that, right? So those are called your priority encoders. And you will have your n output lines from 0 to n minus 1, which is n output lines. So this is also called as 2 raised to n encoder symbol, this symbol. So if a question is asked, you can use this as your answer. Okay, now let me take a different case where you have your D3 and D5. Both are simultaneously 1. Okay, then what will happen is at all 3 output terminals, implying D7 must have been logic 1. Hence, priority encoders are developed. Okay, so that is what I was mentioning here. Say for example 2 and 3. Okay. 2 and 3 is high. So in that case, this logic, okay, whatever we have developed doesn't work out, right? So that is the reason we are using something called priority encoder. Priority encoder means if your D7 is high, then I will not consider any of the values which are below. So there is no confusion at all. Either is it 0 or is it 1, there is no confusion at all. But if I'm not using a priority encoder, then if I have 2 simultaneous ones, then how do I represent here in my output? It's difficult, right? It's difficult. So that's the reason we use something called priority encoders. Okay. So I hope this is understood by all of you. Yes. Have you all understood encoders and priority encoders? Any doubts?
No, sir.
Okay, fine. Thank you for confirming. Next, we will look into something called digital multiplexers. Okay, this was what I was telling you about multiplexers, or sometimes it's also called as data selectors. Okay, data selectors. Fine. So before we move on, just look at the diagram here. You have more inputs and you just have one output. Okay, more inputs, just one output, and you have select lines. Okay, so let us understand this truth table first. So select lines, since I have S1 and S0, so what's going to happen? I have 2 bits, so 2-bit combination from 0, 0 to 1, 1. Okay, and my output Y, okay, my output Y, I'm going to give as I0, I1, I2, I3. Okay, then I have 4 inputs here, as I told you, 0, 1, 2, 3. Say for example, in my S1 and S0, I select 0, 0, and my input 0 is going to appear across my output. Okay, say S1 is 0, S0 is also 0, then whatever is my input 0, this gets passed to my output. So out of these 4 inputs, only one input gets passed to my output. So I am selecting which data to pass from the input side to the output side. Fine. So that's the reason it is called data selectors, multiplexers or data selectors. Fine. So now let us understand the meaning of multiplexing. Multiplexing means transmitting large number of information units over a smaller number of channels or lines. I have less channels. Okay, I have less communication channels, but I have more data to be transmitted. In that purpose, okay, in that scenario, I will be using something called multiplexers. So if I use multiplexers, then what is going to happen? Even though my channel capacity is capable of sending, say I have input of 4 lines, okay, but I have only one channel, so I will not invest my money in buying 3 more channels. So what I will do instead I will employ a multiplexer, and instead of sending all the 4 lines, what I will do, I will just send one line at a time, and I can use only one channel instead of investing on many channels, right? So in this way, what is going to happen, it's going to save my um, cost, right? Cost cutting is happening, and efficient resource utilization also is going to happen, right? Okay. A digital multiplexer is a combinational circuit that selects binary information from one of the many input lines and directs it to a single output line. This is important, to a single output line. The selection of a particular input line is controlled by a set of selection lines. So what are those selection lines? S1 and S0. So these are your selection lines. Say if S1 is equal to 1 and S0 is also equal to 1, then what is going to come? My input 3 is going to appear at my output. Input 3 is going to come at my output. Okay. Normally, there are 2 raised to n input lines and n selection lines whose bit combinations determine which input is selected. Okay. So main important thing here is my select lines. So as per my select line, I will have this input combinations or inputs which are getting selected, and it comes across my output, right? Okay. So how do I implement it? Implementation is very easy, right? So if I draw a function, or if I write a function, okay, function is nothing but I have I0, I1, I2, I3. So this I0, when it is 0, S1 and S0 is bar, which means 0. I1, which means 0, 1. I2, which means 1, 0. Okay, S1 is high, S0 is low. I3, which means S1 is high and S0 is also high. You understood how we got this equation, how we got this function, students?
Yes, sir.
Okay, fine. So similarly, a normal logical implementation we do using inverters, using AND gate and using OR gate. Okay, let's take one example. I0 S1 bar is not bar. So so I0 is no, I multiply I0, then I take my S1 bar, then I take my S0 bar. These are giving my first term. Okay, my first term I am getting here. Second term I get from this. Third term I get from this. The fourth term I get from this AND gate. Okay, AND gate is I3. Then I have to get high S1. Okay, I3 is here. Then high S0 and high S1, right? So this is how we get our multiplexer. In simple, if you want to draw a representation, okay, I0, I1, I2, I3, you will have enable also. Okay, you can incorporate it. You will have select lines, and then you will have your final output. Okay, fine. So students, what we will do here is we will stop here as of now. There is only 2 minutes for the meeting to get disconnected, and then we'll connect after some time. Okay, we'll connect in 5 minutes. Okay, I'll share you the link. Okay, so we had seen the concept of mux, right? And we will be continuing this discussion. So you have this function here, okay, I naught s1 is not bar, and I1 s1 bar is not, I2 s1 is not bar, and I3 when both are high, s1 and s0 are high. Okay, so accordingly we have implemented this logical circuit. Okay, so once this is implemented, I have an option to uh, represent it using this simple block diagram. Okay. Now suppose I want to increase it. Okay, so this is my 4:1 marks. Okay, 4:1 is nothing but 4 inputs, 0, 1, 2, 3, and 1 output. Okay. Similarly, if I use 4:1 marks, I can actually create a 16:1 multiplexer. Okay, so how do we do that? We use 4. Okay, 4 blocks. So you can see here 1, 2, 3, 4, 4 blocks, and each block is the same. It has I0, I1, I2, I3, S1 and S0. Right. So S1 and S0. Here also, for the next mux also, it will have 4 inputs and 1 output. Just that after 3, it's going to continue here. 4, 5, 6, 7. But internally, it is mux. It's a standard mux. So internally, it is I0, I1, I2, I3. Okay, but it is actually the continuation. I3 is here, then I4. Okay, I5, I6, I7. Enable will be high. Enable will be high. It has select lines 8, 9, 10, 11, 12, 13, 14, 15. So I have my 16 input lines. I have my select lines S1, S0. Okay, and then I have my output. So this outputs, again, I will need one more multiplexer because the function f will go into I0, then f1 will go into I1, then f2 will go into I2, then f3 will get into I3. So 1, 2, 3, 4. So 4 inputs are actually taking the outputs from the previous stage, 4 multiplexers. Here also I will have my select lines. Okay, all these are S1, S0, and this will be a continuation of my select lines, which is S2 and S3. Then my final output. Okay, so of course they're not going to ask this for your examination. The main thing, the reason why I have put this is you can extend or you can connect these multiplexers and also make sure that you can create a 16:1 line. Okay, so that is what I wanted to show here. Okay, so students, any doubts here with regards to multiplexers? Any doubts you can ask me. Yes, any doubts here? Okay, Side, yes, I will be sending the notes. Okay, so that is fine, and also I'll be sharing the link for the lecture also. Okay, so basically you should understand that you have this 4:1 mux, and this is your truth table. So question will be like this: what is a multiplexer? Explain the same using your block diagram, your truth table. And some questions could be direct. Okay, they can ask you like implement a mux using logical circuit. So when I ask that question, then this logical diagram that we have here is going to be your answer for that. Okay, very rarely, okay, or I've never seen any questions asked on the 16:1 marks. Okay, but just for your understanding, I have picked up from the textbook given. Okay, remember we have about 3 to 4 textbooks and about 2 to 3 references which I'm using for your subject. So I'm using about 7 to 8 textbooks for this course. Okay, so you will be actually merging them, okay, or you can use 1, 2, 3, 4, 5 multiplexers, and using this 5 multiplexers you can actually implement your uh, your implementation or uh, higher order input value mocks. So tomorrow what I will do is I will start off with the Boolean function implementation. Okay, so this is a new kind of implementation. This is called an implementation table, just like how we saw K-map, how we saw MEV method. Okay, similarly, we have another method. This is called your implementation table method. So using this, how we are going to minimize and how we are going to actually have uh, less number of terms or a minimized equation. Okay, so that is what we are going to discuss in the next class. Okay, so I hope things are clear till this concept that we have discussed, right? And if any doubts, you can always feel free to get back. Okay.